This is AP Calculus BC, and in this video I'm going to talk about section 4.8, which is the mean value theorem. And this is the final application of derivatives that we're going to talk about. This is not so much an application as much as it is a way for us to justify in problem-solving situations things that are often, in a lot of ways, common sense. If you remember back to when we did the intermediate value theorem back at the beginning of the year, I often refer to that intermediate value theorem as the common sense theorem. And the mean value theorem is similar to that. And you'll see after we talk about this, I'll show you exactly what this means in a real life situation. And you'll see that this is something that you really just understand intuitively, but it gives you a mathematical justification for why things are true in certain situations. So for the mean value theorem, the first part of this, what I did was I put an exploration in your set of notes. And the exploration is supposed to give you just a graphical understanding of what exactly is going on when we talk about the mean value theorem. So what we're talking about here are situations where we're looking at average rates of change and instantaneous rates of change. So when we talk about an average rate of change on a graph, remember that is the same thing as the slope of the secant line. And when we talk about an instantaneous rate of change, that's the slope of the tangent line. So on this exploration, I'm going to have you work through most of this. I'm going to show you the first problem, and then I'm going to have you pause the video. I'm going to let you work through the rest of these, and then I'll just briefly go through the solutions, and it'll give you an understanding of what we're getting at here with the mean value theorem. So this first problem, there's a cubic function, and it says we're looking at the interval between 3 and 7, and they ask us to do a few things here. It says draw the secant line and the tangent line, and then what is C approximately equal to? So I'll explain what they mean by that. So the first thing is, if I draw the secant line, notice on this graph they have 2 points here, at 3 and at 7. So I'm going to draw a line going through those points. Okay, so the slope of that line is my average rate of change on the interval between 3 and 7. Now, what the mean value theorem is getting at is the idea that at some point, if my function is differentiable and continuous on this interval, at some point the average rate of change has to equal the instantaneous rate of change. And if you notice here, if I translate this line up, then out here, somewhere around here, it looks like I've got a point of tangency, and at that point, my average rate of change is equal to my instantaneous rate of change. So that happens at roughly 5.6. Okay, and then it says, is the function differentiable on 3 to 7? Well, this is a cubic function, so yes, it's differentiable everywhere. And is the function continuous on the closed interval from 3 to 7? And the answer also obviously is yes, because it's a polynomial function. So that's what I want you to do for the rest of these problems in this exploration. So I want you to pause the video, go take 5-10 minutes, go through the rest of these. And then when you unpause the video, I'll explain what exactly we're trying to get to by going through all of these exercises. So go ahead and pause the video, and when you come back, I'll show you the solutions. Okay, so here is what you should have ended up with for number 2. So we have the same function. This time we have the interval from 1 to 7. And if you notice, this time we actually have 2 points where the average rate of change is equal to the instantaneous rate of change. But again, this function was differentiable on the open interval. It was continuous on the closed interval. Number 3, now we've got a function that has a cusp in it. So they ask you to draw the secant line between 1 and 5, which is done there. But is the function differentiable? No, it's not this time, because you have a cusp inside the interval. And is it continuous? Yes, it is continuous. However, notice this time there's no point within that interval where the average rate of change is equal to the instantaneous rate of change. So the slope of the secant line is never the same as the slope of any tangent line on the interval from 1 to 5. Okay, so here's the next problem. So same graph, the only difference is this time we're looking at the interval from 1 to 4. So that cusp point is one of our endpoints this time. So notice this time the function is differentiable on the open interval between 1 and 4 because we're not including 4 as part of the differentiability. and the function is continuous between 1 and 4. So this time both of those answers are yes, and we do have a point where the average rate of change is equal to the instantaneous rate of change. All right, the next one, we've got a piecewise function, and you notice here we've got this jump discontinuity at the point where x is 5. And the first interval they have you look at is 5 to 7. So is the function differentiable between 5 and 7? And yes, it would be, because we're only looking at the right branch of that function. But is the function continuous on the closed interval, meaning including the endpoint at 5? And the answer would be no, because of that jump discontinuity. So if you draw in your secant line, you can see that there's no tangent line that would be parallel to your secant line in that case. All right, so same graph again. This time we're looking at the interval from 5 to 9. So notice for differentiability, we're only looking at the right side of this interval. Is the function continuous? Well, is it continuous? No, it's not, because again, we're looking at that left endpoint at 5. But this time it happens to turn out that the average rate of change is the same as the instantaneous rate of change at one point within the interval. And then the last one here, number 7, same graph, but this time we're only looking at the interval from 1 to 5. So we're only dealing with the left branch of this piecewise function. And in this case, yes, the function is continuous. Yes, it's differentiable. And now we do have a tangent slope that is the same as the secant slope at some point within the interval. So here's what the mean value theorem says. The mean value theorem says that if a function is differentiable on an open interval and continuous on a closed interval, then there's some number within that interval such that, and you see this in mathematical notation, f prime of c is equal to f of b minus f of a over b minus a. That's essentially saying the average rate of change, which is the f of b minus f of a over b minus a, is equal to the instantaneous rate of change, that's the f prime of c, at some point c within the interval. And if you go back and look through those, you can see that in 4 of those examples, we did have the hypothesis of that theorem to be true, meaning the function was differentiable on the open interval and continuous on the closed interval. We also had some where both the hypothesis and the conclusion were not true. But then there was one situation where we still had a point where the average rate of change was equal to the instantaneous rate of change on the interval, even though the function was not differentiable and continuous. So the main point is, if I meet the conditions of the mean value theorem, meaning the function's differentiable on the open interval and continuous on the closed interval, then I'm guaranteed to have a point where the average rate of change is equal to the instantaneous rate of change. It can still happen to be true in certain circumstances, but I'm not guaranteed for it to be true unless I meet the criteria of the mean value theorem. Okay, so let's talk a little bit about how we're going to use this. So primarily for us, we're going to use this as a problem solving and problem justification in our problem solving situations. So this is just a restatement of the mean value theorem. And you can see this is the way I typically state it. There's at least one point on the interval where the instantaneous rate of change is equal to the average rate of change. But you always want to keep this setup in your mind. So what it says right here, that should always be what we're thinking about. And then when you read that in your head, you should be thinking, oh, f prime of c is instantaneous rate of change. F of b minus f of a over b minus a is the average rate of change. Okay, so here are just some examples, a couple of functions plotted, and you can see that when we have the criteria of the mean value theorem being met, notice that it says there is at least one point where that's true. So you can have more than one point, and it really depends on your function. So you can see this graph on the right, this one over here, and we had one of these like that in the exploration that you went through. It is possible you're going to have more than 1 point. So in this case, we had 2. You could have 3 or 4 or 5. It just depends on what your function looks like and what interval that you're looking at. All right, so here's a really basic example. This is what a lot of the basic mean value theorem questions are going to look like. So it says, given that the function f of x is 2x squared on the interval from -1 to 2, is the hypothesis of the mean value theorem satisfied? So remember, the hypothesis is the function differentiable on the open interval -1 to 2? The answer would be yes, because it's a polynomial. is the function continuous on the closed interval, meaning including the endpoints, -1 to 2? And again, the answer is yes. So is the hypothesis satisfied? The answer would be yes. So then the second part, find the point C where the slope of the tangent line is equal to the slope of the secant line between -1 and 2. So again, what we should be thinking about is we need f prime of C to be equal to f of B minus f of A over B minus A. Okay, so fairly simple. Now, in our case, for this particular problem, f prime of x is equal to 4x. And we also know in this case that b is 2 and a is -1. So if I plug c into that derivative, I get 4c. That means 4c has to be equal to f of b would be 8, because 2 times 2 squared is 8, minus, if I plug -1 into that function, I get 2. And that's divided by my change in the x values, which would be 2 minus -1. And that gives me an equation that I can then solve for c. And it turns out here that c is equal to 1/2. Now, sometimes when they ask you for the c value, they're just going to be talking about the x coordinate. Sometimes they're going to want the x and the y. So I'm just going to give the overall point here. And it really just depends on the way the question is worded, whether or not you need to get the coordinate or just that actual x value. Okay, so in the end, it's a fairly simple process. This one was really easy because the derivative was simple. The algebra to solve for c was very, very simple. You'll have a lot of questions where the functions are going to be messier, but the process will always be the same. Okay, your derivative might be messier. When you start solving for c, it might be a little bit of work, but this is the overall process. So I'm not going to go through all of the particular types of algebra that could show up. But just keep in mind that this is the main idea, and once you've gotten your derivative, it just turns into an algebra problem. Okay, so let's talk about why this is actually useful to us. And I'm just going to go to the bottom of this last page and just talk about this for a second before we get into the special case of mean value theorem. So let's say we had a problem, for example, where we were looking at somebody that was driving from Austin to Waco, and we'll say that's roughly 100 miles. Okay, so we're going to drive from Austin to Waco. Okay, and we'll say that's approximately 100 miles of driving. Okay, so let's say it took 75 minutes to get there. Okay, so what would our average rate of change be? Well, our average rate of change would just be, and I'm going to do this in miles per hour, it would be the 100 miles, and that would be over 1.25 hours, and that would give us an average of 80 miles an hour. Okay, so now, again, remember, this is really common sense. The highest speed limit, let's say the highest speed limit between here and Waco is 70 miles an hour. Did the person driving speed during the time interval that they were driving from Austin to Waco? And obviously the answer is yes, right? Just common sense. Yes, they definitely sped because their average is 80 miles an hour. But the mean value theorem is what I use as my justification. So the function, the position function of me driving from Austin to Waco is a function that is continuous and differentiable on the entire time interval. I can't skip from one position to another position. I can't teleport from one spot to another on the road. So it's a continuous function. It's differentiable. I have to be driving a certain speed at any point along the way on my drive. So it meets all the criteria of the mean value theorem. So at least one point on my interval, my average rate of change had to equal my instantaneous rate of change. So for at least one point in time, I had to be driving 80 miles an hour. And obviously, for several points in time, I was probably driving 80 miles an hour because there were probably times I was driving faster than that, times I'm driving slower than that. But what the mean value theorem says is I'm guaranteed to have been driving 80 miles an hour at least at one point in time. Okay, so again, common sense, but now you have a mathematical justification for something that before you would just describe as common sense. Okay, so the last thing we're going to talk about here is called Rolle's theorem. And Rolle's theorem is really just a special case of the mean value theorem. So Rolle's theorem has to do with when our average rate of change is equal to 0. So it says let f be a function that satisfies the following hypotheses. F is continuous on the closed interval, same thing as mean value theorem. F is differentiable on the open interval, a to b, same thing as before. But now it says at the endpoints, f of a is equal to f of b. So what that means essentially is my average rate of change is equal to 0. Then there has to be a point C in the interval a to b such that the average rate of change is equal to 0. Okay, so it's really simple, and it's just a special case. So let's look at a couple of examples. It says find the two x-intercepts of x squared minus 3x plus 2 and show that f prime of x is equal to 0 at some point between the two x-intercepts. Well, if we're going to find the x-intercepts, we would just take x squared minus 3x plus 2, and we'd set that equal to 0. You can factor it and solve it, and you'd get x is equal to 1 and 2. Those are my two x-intercepts. So what that means is f of 1 is equal to f of 2, and those are both equal to 0. Okay, so how would we show that f prime of x has to be 0 at some point within the interval? Well, whenever we're going to use the mean value theorem or Rolle's theorem, it's just like the intermediate value theorem. If you're going to use the theorem, you have to essentially restate the theorem. So I don't want to actually necessarily say the name of the theorem because that's not really the important part. Yes, it's good to know that we're using the mean value theorem or Rolle's theorem, but if you state what the theorem says, then knowing the name of the theorem is not even necessary. So how I would justify this is I would say f of x is continuous on our closed interval 1 to 2, because that's the interval for the points that we just evaluated. And we know f of x is differentiable on the open interval 1 to 2. So we know for sure f prime of x has to be 0 at some point on the interval. And it's in the interval 1 to 2. And we know that because those two values that we just found, f of 1 is equal to f of 2, which was equal to 0. Okay, so it's a little bit of work to write out your justification. However, it's one sentence. We've got everything about the mean value theorem and especially Rolle's theorem stated here. And so we know that we can then be guaranteed that there's a point where the instantaneous rate of change of this function or the derivative is equal to 0. And if you think about it, it makes sense, right? It's a quadratic function. If I look at the two zeros of that quadratic function, this is a quadratic that's opening up. So think about graphically what exactly is that saying. Well, just here, I'll do a little quick graph. Let's say here's our two x-intercepts. We know it's a parabola that opens up. And so what this is saying is between those 2 points, there has to be a point where the tangent slope is equal to 0. And so that's where the C value would be in this case at the vertex. Okay, so that's really what we're looking at. Now for something like a polynomial, it's pretty obvious. When functions are a little more complex, this can be useful for us because we don't necessarily have to find those points to prove that they actually exist. All right, so the last problem here, it says prove that the equation x cubed plus x minus 1 has exactly one real root. So we're going to use Rolle's theorem. We're going to use it in a little bit different way. So let's define our function. So let's say our function is x cubed plus x minus 1. If I take the derivative, in this case, I'm going to get 3x squared plus 1. Well, think about that. Is that ever going to be 0? Okay, so I would get, if I solve that, x squared is negative 1/3. And in that case, there's no solution. So with no solution, that means that f of x is always increasing. Okay, so we know the function's always increasing. And so how do we know there's exactly one root? Well, we know there's exactly one root because f of b minus f of a over b minus a cannot be equal to 0 for any point or for any values for any AB that we could possibly use. So any real values of A and B, there's never going to be an interval where the average rate of change is equal to the instantaneous rate of change. Now, I could go through and say this is a function that's differentiable and continuous if I really want to be technical about it. But the main thing is I've got a function that's always increasing. There's never going to be a point where the slope's equal to 0. So that means the function can't change direction. And since it's a differentiable function, and that then tells me that there's only going to be one real root. Okay, so as far as the homework goes, a lot of the problems are going to look like this one that I showed you earlier. Let's see, right here. So this one that I showed you earlier. So with the f of x equals 2x squared, like I mentioned before, when you do these problems, you're probably going to have functions that are a lot more complicated. The derivatives are going to be messier. When you solve out and set the derivative equal to the average rate of change, it's going to be a messier process. But overall, that's essentially what you're trying to do. And then the other thing is just remember, if you're going to use the mean value theorem or Rolle's theorem as a justification, and this is going to show up on your test, this is going to show up on the AP exam. If you're ever going to write out and use this as a justification for an answer, you have to write out a statement like I wrote out on this one here.